Good evening, everyone. I'm Bala, and the topic that I would be presenting would be on a selective sensor framework, which uses sensor fusion to achieve task and decision execution. The overview of today's presentation would involve an introduction to HRI, that is human-robot interaction, and a multi-sensor fusion, followed by the different architectures of multi-sensor fusion, the fusion algorithm called the Dempster-Shafer theory of evidence, the speech processor, the sensor manager and the task manager, which are the novelties of this work, the decision framework itself, and the assist phase and conclusion. HRI, as the name suggests, is about interacting with vehicles, right? So the purpose of having a HRI is to improve the task performance, improve the overall throughput of your system in terms of interaction, and to reduce the burden of the user or the operator. And sometimes, since humans cannot operate in difficult environments, we need vehicles to just walk around, but also even communicate with them as a peer. Some of the famous examples are the Raven robot, which is a surgical robot, the Bear robot, as shown as in the figure, which is used in military rescue operations, and the Robonaut. Multi-sensor fusion, as the name suggests, is collecting data from not just one sensor but from different sensors to improve the reliability of our system and to make sure that there's a timely response based on the several inputs. And this makes our system more robust and more resilient in terms of faults and performance. The centralized fusion architecture is something that's, as the name suggests, there is a single fusion node. Each of the sensors can do their own local pre-processing, that is noise filtering and correction, and you have the alignment, association, and the estimation. This falls under the terminology called as the common representation format, wherein you convert all the data into the corresponding local frame, and then do the corresponding association and finally estimation. In the distributed sensor fusion architecture, each of the nodes do their own local processing and fusion, and then there is still a centralized node that has a global view of your system, which still performs its own alignment, association, and estimation. The Dempster-Shafer theory of evidence is a kind of an inference-based algorithm, or more than an algorithm, it's an inference-based method, wherein you have an hypothesis, say H, and or S, and you have 2 to the power of S different combinations of that, and there are certain restrictions as described by the theory itself, as you have the belief of the entire set has to be 1, and to support any hypothesis you should combine all the mass functions which support that particular hypothesis. And confidence interval basically represents the lower and the upper bound of your probability of that particular hypothesis. Like for example, if M1 and M2 are mass functions and you have 2 sensors which are giving this value, then you have something called as the rule of combination as shown by this equation. The denominator is basically the normalization constant, which can or cannot be used depending on your application. This project basically talks about a human-machine interface which uses speech as the front end of the system. Then you have a sensor management system which uses the concept of sensor maps and task map in order to come up with a framework, and then that framework finally uses Dempster-Shafer at the end in order to come up with a decision. The assist phase is something that is like a help phase to support two-way communication between the robot and the user. The front end of the system, as it says, is the speech processor. You have a high-level task command, and this command is actually decomposed by the speech string decomposer into low-level commands. For example, move from A to B and do this operation will be decomposed into 2-level commands. The sensor map is kind of a concept similar to the taken from the sensory brain map, wherein we have different slots for each of our sensors on the surface of the brain. So the sensor 1 observation, if you can look at that line, it says the entity measured, the usage, position, measurement vector, and so on. These are all the parameters for each sensor. Each sensor will have those parameters. The sensor selection procedure is important because it kind of does the selective sensor fusion, wherein you take only the sensors required for a particular task and switch off the sensors that are not required for your current task. They can still be measured but are just not used for your equation, the combination equation. And priority assignment is something similar to assigning weights for 2 purposes. Either it reduces faults in your system, and secondly, based on a heuristic of your application, you can give more weights to a particular sensor than the other sensors. The sensor map is like a data structure, and you need an entity to actually manage that structure. So you have the sensor manager, which will keep track of the usage of the different sensors in your system. And since it's based on the sensory brain map concept, it uses the use it or lose it principle. When a particular heuristic is not satisfied by a sensor, that particular sensor the space for that sensor is actually dynamically reallocated to another existing sensor. This improves the performance of the existing sensors and gives more space to new sensors. The task map is another structure similar to the sensor map, and since we are dealing with a high-level task planning, each task is actually decomposed into subtasks. And similar to the sensor slot, sensor observation slot, you have a task one slot, which has the task name, the priority, the dependency, and since each task, since you're using selective sensor fusion, each task depends on sensors, right? So you have sensor dependency vector for each of the tasks. The task manager is an entity which actually controls our task map, and it updates the usage statistics of each of the tasks, and it does a task-based reassignment, again depending upon the application-specific heuristic. And when a particular task is not used, it can disable and finally delete the task. Another thing is that since we're using a speech as front end, we can even train new tasks into the system, and we can add new tasks to the task map. This is the overall system. The user input is something that can include the map of the environment or any constraints which will form the soft data set. And the sensor inputs will be something that we cannot control, which is from the physical sensors, and it's the hard data set. And the pre-processing and data fusion includes the data fusion algorithm as well as the sensor correction, that is alignment association. The constraints check is a block that makes sure that even though we have a decision, it matches with the kinematics of the vehicle or other dynamics of the vehicle. And finally, you have the action, which is the what we want the vehicle to do. The assistive phase is actually a representation of the collaborative control, wherein we want the robot to not just walk around and just do a pre-programmed operation, but to even communicate with the user. So, so that's why we have a two-way communication for this, two-way communication module. And similar to log messages, we have different severity levels for different issues depending upon our application. Like for example, I give a constraint, and if the vehicle goes out of that constraint, I do a time exceeded help number. And sometimes if it's physically stuck, I cannot move, then it has its own help number. So. Now a simple example would be of a high-level task to take a package and to deliver between two different points, say A and B, and you give a time window, say T time units, and like we have a user input that can include the different points of the map with static obstacles as well as the source and the destination locations. We can assume how the physical vehicle to be having 4 wheels, non-holonomic, which means it can steer in all directions, and it can have distance sensors and a camera. Now, how the speech input can be is like deliver a package from location A to B or X to Y and give it to a person B. Now, the speech processor, if you can look at it, it will decompose this into two different commands, namely like deliver a package from A to B, which will be a path planning phase, and then give it to a person B, which is basically an image, a phase that actually depends only on the camera for recognizing the person. So this the speech decomposer will handle this high-level task string, and then it maps it to the subtask or the sequence of commands. And then even the path planning, for example, A to B can be decomposed into A to C and C to B. You can even give this as a task map, or you can even do a dynamic path planning algorithm, which can be run as a separate module when you're doing this. Now, we talk about the sensor selection phase, right? So we have, for example, move forward, we need only the sensor data and the camera data. So they form one group, and the other sensors will form a different group, but they still be sampling the values, but you just will not be using it for your fusion algorithm. Now, once you do all the sensor corrections and you run the fusion algorithm, if there are no obstacles, you just keep moving forward as the task says. And suppose if the front camera recognizes the person, you will have an image repository where you can actually get the check for the person in view in the field of view. If it recognizes, then it signals task completed. If not, then it enters into the assist phase. So we previously saw different help numbers, right? So for example, human in front of the vehicle and unrecognizable, so it actually goes into the assist phase. In the assist phase, as we saw, we have different severity levels, and we can give speech, or you can also have a pre-processed or another function which handles each of those severity levels. And when the robot can't identify the person, it can actually query back with the user through a wireless communication or some other protocol and get advice from the operator. And then the vehicle, since we can't keep waiting indefinitely, you should have a timeout interval. And if the timeout doesn't happen, then it receives the response from the user. If a timeout happens, then you can just abort the operation, or depending on how you can program it. It's an implementation level detail. Once it reaches the final destination, location B, say, it checks for the person in the field of view. If there's a match, then it actually signals the packet delivery. If not, then it still signals task completed because it did finish 50% of the task. It's something that you can actually change on the fly. And it says, but it does say the person wasn't found. Overall, we saw how to apply selective sensors for the fusion, and we introduced the concept of sensor map and a task map, and how this sensor management system actually depends on the sensor map and the task map in order to do a task execution and to do a task planning. The assist phase, which was an indication of how you communicate between the robot and the user as a two-way collaborative control. And then you had constraints check to make sure that you take care of the physical limitations before you execute the task. So here are the differences.